Duncan Foley and Lance Taylor have worked both separately and together using a variety of creative tools and approaches on the macroeconomic implications of climate change. One of their outstanding features, indeed, is their creative and often innovative search for whatever tools and approaches will be most useful in finding real answers to real problems. While Lance was teaching political economy of the environment at the New School in New York, Duncan worked on dynamic growth models with multiple capital goods, which would eventually lead to his research on global warming. In the past several years, they've co-authored papers on the social cost of greenhouse gases and pushed forward the frontier of environmental macroeconomics, anchoring their models on national accounts and other databases, very much in the spirit of Wassily Leontief. Lance built his models off of social accounting matrices of national economies, while Duncan studied the informational content of constructs such as GDP. Both of them have gone beyond economic research, Duncan into physics and Lance into practical policy, especially in developing countries. As an example of their interlocking and overlapping interests, Duncan contributed a paper to the 2003 book, Development Economics and Structuralist Macroeconomics, Essays in Honor of Lance Taylor, while Lance was co-editor of the collection Social Fairness and Economics, Essays in the Spirit of Duncan Foley. And they both contributed essays to a 2009 book that Jonathan Harris and I edited called 21st Century Macroeconomics Responding to the Climate Challenge. So I'm going to start by introducing Duncan, who will speak first. And I think we will hold questions to the end. Is that, yeah. All right, so Duncan Foley has contributed path-breaking papers to almost all fields of economics. His work on Bayesian statistics has led to many advances in non-parametric econometrics. His first Econometrica paper raised problems concerning the treatment of time that neoclassical microeconomics still struggles with. His work on Marxian economics put capital in a modern form, offering an accessible and rigorous introduction to Marxist thought. From the start, he recognized the importance of money in the economy, an issue that is oddly missing from many macro studies. As an educator, he has emphasized the value of using mathematical and statistical models to treat economic problems, and also the importance of taking research questions to the data. Duncan persisted in making a deep exploration of what is really going on in the standard Marxian model, in spite of the sometimes unfavorable atmosphere for that, emerging with an ability to compare it to the standard neoclassical model. His explorations of Adam Smith, Say, Keynes, Straffa, Minsky, as well as complexity, chaos, and other recent ideas, gives his work extraordinary breadth and depth. He's made contributions to growth theory, business cycle theory, and the theory of distribution, and more recently has taken up environmental questions, mostly in a macroeconomic context, and has co-authored much of his subsequent work on the environment with Lance. His publications span the fields of public finance, macroeconomics, money, Marxian theory, economic dynamics, neo-Ricardian economics, growth theory, and complexity systems theory. His recent work includes studies of the relation of statistical mechanics and thermodynamics to economics. His two most recent books are Unholy Trinity, Labor, Capital, and Land in the New Economy, published in 2003, and a 2006 book on the history of political economy and economics, Adam's Fallacy, A Guide to Economic Theology. And I am looking forward to hearing what he has to say to us today.
My first serious discussion of these problems was with Graziella Ciccioniski and Jeff Heel at Columbia University in the 1990s, which led to my participation in several workshops and conferences they organized. In November 2006, Neva Goodwin and Jonathan Harris invited Lance Taylor and me to participate in a workshop on environmental economic problems, including climate change, which gave me an opportunity to summarize the conclusion that I had reached, that if business as usual paths are inefficient, there are no opportunity costs to correcting global warming, and in fact, that correcting global warming represents a net gain in welfare to the global economy. Arman Rizai, who is here, then a graduate student at the New School for Social Research, collaborated with Lance and myself in elaborating this point of view through the development of a growth model with climate damage, which exhibits and roughly estimates the net gains to the correction of global warming. This work was published in the journal Economic Theory in 2010. I should also mention a little bit further back in the history, Marty Weitzman, who both was my classmate at Swarthmore College and shared an economic theory seminar with me when we were at Swarthmore. And even more pertinently, it was some of Marty's work on the problem of the commons and the question of average cost and marginal cost pricing that largely made a big impression on me and informed my theoretical point of view about this. So it's delightful to have him here. Arman and Lance are wonderful people to work with. Arman saw implications of the welfare economics point of view that greatly expanded the significance of these initial insights. Lance is an acute and astute critic and has the uncanny ability to know the answers to quantitative questions before they have even been posed. I am delighted to be sharing this prize with Lance. It is very commonly assumed that climate change can be brought under control only by means of a sacrifice on the part of present generations. For example, the Stern Review recommends the present generation make a small reduction in its income, perhaps 2%, in order to bring about a much larger increase in world income in 150 years' time. Bill Nordhaus's optimized program also shows a reduction in present income, which generates an increased income in the future through a reduction in climate damage. But actually, no sacrifice on the part of current generations is necessary. Climate change can be controlled without a sacrifice on anyone's part of their material economic welfare. Because the emission of greenhouse gases that leads to climate change and climate damage is what economists call a negative externality, the business as usual path on which the world makes no effort to control climate change is inefficient. Correcting this externality, whether through imposing a carbon tax or establishing a system of tradable emissions permits that lead to a positive real cost to emitters of greenhouse gases, or through direct regulation of emissions, will create a net economic surplus that can be divided in a variety of ways between current and future generations and among the various regions and classes of the world economy. In immediate practical terms, even though reducing the emission of greenhouse gases does require real resources that could be used for other purposes, a policy of taking those resources from conventional investment yields net benefits. And this is the hard part for people to get their understanding around, I think. And the reason for that is that the reduction in, that the benefits to the future generations from the reduction in emissions more than offsets their costs, the costs to future generations of a smaller conventional capital stock. Thus, it is possible to reduce greenhouse gas emissions and either maintain or increase the standard of living of current generations without inflicting economic costs on future generations. The growth model Arman, Lance, and I developed to estimate the magnitude of these effects suggests that a diversion of less than 2% of world output from conventional investment, which currently runs about 25% of world output, to investment in greenhouse gas mitigation would raise long-run world income per capita significantly and achieve close to pre-industrial levels of greenhouse gas concentrations in the atmosphere over a time horizon of 200 years. While 2% of world output is, as they say, real money, depending on your estimate of world output, perhaps $1 to $1.5 trillion at current prices, it represents a manageable reallocation of resources on a global scale. If we are ingenious enough to make sure that this diversion of resources comes at the expense of relatively low-yielding conventional investments, and to compensate the losers in a switch from fossil fuel energy to renewable energy sources, current generations need experience no reduction in standard of living as a result. This is the theory, as I'm sure you're all saying to yourselves. Can we make it pay out in reality? Let me speak a little bit about free lunches. Since the 1980s, economics as a quasi-science has appeared in public discussion primarily in the guise of a hard-headed realism, insisting that policy choices involve trade-offs, winners and losers, and budget constraints. This heritage of the TINSTAAFL, Tinstaffel, which means there is no such thing as a free lunch dogma promulgated by free market enthusiasts, unfortunately is at best a half-truth and has seriously confused public perceptions of policy options to deal with climate change. The half-truth in the Tinstaffel doctrine is that human beings can only work with the resources they have and their own ingenuity to solve problems. These aspects of finite mortality do impose ultimate limits on human action and social policy. The fallacy of the Tinstaffel doctrine is its implication that actual institutions, policy, and behavior are always somehow sure to reach the frontier of the feasible set defined by resources and technology. This is far from the truth, even under the most aggressive free market policy regimes imaginable. The discussion of climate change policy has suffered greatly from the distorting effects of this free lunch kind of thinking. It has led us to believe that there must be trade-offs to be faced in climate policy, which on careful examination prove not to exist in reality. The most pernicious of these fallacious trade-offs is the view that climate change is an intergenerational conflict in which the interests of current generations have to be sacrificed for the benefit of future generations. As I have just argued, the reason climate change does not lead to intergenerational or any other economically meaningful conflict is that the burning of carbon-based fossil fuels is a negative economic externality. When someone decides to burn carbon, they consult their own interests in trading off the benefits of the energy they reap against the costs of the fuel. But they do not take account of the costs they impose on others, in particular by adding to the atmospheric stock of carbon dioxide. As a result, human society operates at an inefficient status quo ante in relation to greenhouse gas emissions. In terms of the free lunch doctrine, we fail to reach the frontier of feasibility in managing energy production and the risk of climate change. One implication of the welfare economics of climate change is that correcting the greenhouse gas externality is an economic benefit to be distributed to human beings of current and future generations, not an economic cost that has to be met by some pattern of shared sacrifices. I'll spend in a moment discuss how the fact that, curiously enough, may not make it any easier politically to deal with it. Controlling climate change need have no negative effects on any relevant economic outcomes, for example, growth, employment, or standards of living. One paradox of welfare economics, however, is that the distribution of a potential benefit can be more problematic than the imposition of an inescapable cost. When human society as a whole or some part of it faces an externally imposed inevitable loss, there's a natural disaster or some part of the capital stock is just destroyed, it is likely that the result, whatever heroic sacrifices or selfish opportunism intervene, will not be any further from the shrunken frontier of feasible outcomes than the status quo ante was from the original frontier. Somebody has to take the hit, but there's no point in making things worse than they have to be. On the other hand, history is replete with examples of potential mutually advantageous changes that fail to be realized because the participants cannot agree on how to divide the gains. As a result, no one may reap any share of potentially large benefits. Climate change threatens to fall into the second category. Let me say just a very few words on the practical, moving towards the practical policy implications, and then I'll close with some inspirational peroration here. Weaning the world from carbon-based fossil fuels is a significant challenge. It is not, however, an unprecedented challenge in historical perspective. The enormous investments and changes in life precipitated by technical innovations such as steam power, electricity, and information processing are at least as large and far-reaching and have resulted in gains and losses of welfare on an equal or larger scale. Concretely, the main negative economic consequence of restricting fossil fuel energy production will be the devaluation of fossil fuel reserves, the accelerated depreciation of fossil fuel-linked investments, such as gasoline-powered automobiles and carbon-based heating and air conditioning systems, and a permanent rise in energy prices. To implement a policy of climate change control without any losers will require compensating these losses. How would this work? Consumers and producers facing high energy prices will spontaneously defend themselves as much as they can by substituting toward lower energy and lower carbon alternatives. Suburban sprawl will give way to more compact urban development, square feet of living space to better views, aluminum containers to cardboard, commuting automobiles to bicycles, and so forth. These defensive readjustments, what economists call substitution, will inevitably, however, leave consumers and producers worse off in purely material terms than before the rise in energy prices. These losses will have to be compensated, for example, by increased consumption of goods produced without fossil fuel energy. One person who brought these concerns to my attention was Julie Nelson, actually, after the 2009 workshop. Such an increase in consumption can be achieved given the productive capacity of society at any time period by reducing resources devoted to investment. But wouldn't this be bad for economic growth and the welfare of future generations who would inherit a smaller capital stock as a result? Considered in isolation, a shrinkage of investment does hurt future generations. But as I've already argued, considered as part of a package that includes lower climate damage, a policy of diverting resources from investment to non-carbon intensive consumption can improve the welfare of future generations. How could a shift from investment to consumption in order to compensate consumers and producers for higher energy prices be financed? One policy is to lower taxes on current consumers and producers and finance the resulting shortfalls in government revenue by borrowing. But won't that increased borrowing burden future generations with a larger debt? The usual economic argument against financing consumption expenditures with government borrowing is that the government borrowing crowds out productive investment. But as we have seen, the goal of climate change policy is precisely to shift resources from low-yield conventional investments to consumption to compensate for losses imposed by the transition away from fossil fuel energy. Crowding out is an economically efficient way to do this because it works by raising interest rates on private borrowers and therefore eliminates the lowest rate of return private investments in an efficient manner. The issuance of debt to finance tax relief to compensate consumers and producers for a rise in energy prices is a way to ensure that future generations will not appropriate too large a part of the increases in welfare that controlling climate change delivers. Future generations effectively pay the current generation to restrict carbon emissions by paying the interest on the debt incurred. This logic, a policy economist knows, as policy economists know, however, in the real world, this theoretical argument often fails to lead to welfare-enhancing policies, in this case, emissions control to limit climate damage. Even when the fiction of the typical consumer is roughly correct, as in investments in infrastructure for transportation or public health, which presumably benefits individuals fairly uniformly, it is not easy to secure political support for expenditures. So I would argue the political challenge of climate change is most accurately conceived as the problem of designing compensation and mitigation schemes that a reliable, large majority of polities will support. Therefore, it's a combination of craftsmanship in policy and entrepreneurship in politics. The skewing of political power that results from high inequality in the distribution of incomes and the disproportionate influence of well-organized business interests on legislation does not make this task any easier. But even with these hard political constraints, there is good reason to believe that politically viable and environmentally effective schemes for mitigation of climate change are feasible. It is a question of deciding, in my view, to roll up our sleeves and do something about it and actually address this problem of climate change, which is a big challenge, but human beings are used to taking on big challenges, and I think we can do it. Thank you.
I think I forgot initially to thank the Tufts Institute for the Environment, who have co-sponsored this event. So I just, while I think of it, wanted to make that point. So about Lance Taylor. He was a major figure in the invention of modern computable general equilibrium models, giving him a brilliant insider view of their limitations and of the harm they could do when wrongly used. A review of his 2009 book, Reconstructing Macroeconomics, Structuralist Proposals and Critiques of the Mainstream, gives a nice overview of his position. It said, macroeconomics is in disarray. No one approach is dominant, and an increasing divide between theory and empirics is evident. This book presents both a critique of mainstream macroeconomics from a structuralist perspective and an exposition of modern structuralist approaches. The fundamental assumption of structuralism is that it is impossible to understand a macroeconomy without understanding its major institutions and distributive relationships across productive sectors and social groups. Lance Taylor taught economics at Harvard from 1967 to 74, and at MIT from 74 to 93, and then elected to look for places that were more congenial to his perceptions of the world, including, of course, his beloved farm in Maine. During approximately the first half of his career, he wrote important studies on Argentina, Brazil, Egypt, Mexico, India, Nigeria, and Nicaragua, sometimes collaborating with another of our former Leontief awardees, Jose Antonio Ocampo. He is currently Emeritus Professor of Economics and the former Arnholt Professor of International Cooperation at the New School for Social Research. As an educator, he has emphasized the importance of classical economics as a treasure chest containing almost all ideas discussed in subsequent centuries. His most recent book, Maynard's Revenge, The Collapse of Free Market Economics, emphasizes Keynes's point that we don't really know what's going to happen in the future, and that the current state of the economy results from the confluence of financial deregulation and worsening income inequality. In recent years, Lance has turned to environmental questions, researching ways to introduce factors such as the social cost of carbon emissions into demand-driven models. Perhaps his most famous contribution to macroeconomics, although I'm a little, I'm not confident that I should be saying what is his most famous contribution, but I want to mention the demand-driven models, which have shown that social relations are critical to the working of any macroeconomic model, as they shape the behavioral rules determining a system's performance. His macro models have had a strong influence on the policy debate, especially on topics such as stabilization, income distribution, and trade liberalization. And I welcome Lance Taylor here and look forward to what he will be saying to us. So we'll trust that your clip will...
I think it's on.
I think it is.
which was pure luck. Well, thank you, Neva, very much for that kind introduction, and thanks to Duncan for telling me what to do right in terms of economic theory when we play with these climate issues. What I'd like to do is take a slightly different approach from Duncan's in discussing greenhouse gas emission and its implications for how the economy is going to operate. That is, I want to start really from the side of demand, in a demand-driven model, demand-driven growth model, and ask how the world is going to respond over a period of, say, a couple of hundred years to the growing threat of greenhouse gas emission. Now, of course, talking about 200 years is absurd. We really have no idea what the world is going to look like even a few decades from now, let alone quite a few centuries from now. But I think it's important to take a long-term view. And what we've done jointly with Duncan in the model I want to talk about is try to guess what the implications would be and what would be the benefits of trying to do something about it. Now, someplace should be a computer here with an arrow key. Yes. So what I want to do is talk about results from a demand-driven model involving greenhouse gas concentration, that is G up there, and the capital population ratio, that is how much capital there is per population in the world. And the big result, if you look at these diagrams here, the black line shows business as usual scenarios from this model. And basically what it does is show that you can get some growth for a period of a few decades, say 6 or 7 decades. Then there's an abrupt crash in the level of most of these variables: capital stock per capita, output, employment, other variables. At the same time as greenhouse gas concentration shoots up, again, beginning in the second diagram at the top to the right, greenhouse gas concentration shoots up, and then it doesn't go away. And that's sort of the story that we have that we built into this model, and which I think is actually fairly relevant. Now, you can try to offset that by mitigation in one way or another, and that could take various forms: reinjection of carbon dioxide into the ground, replacement of fossil fuel by other sources of electricity, et cetera, et cetera, et cetera. And given the current estimates of the cost of mitigation, if you say spend 1% or 1.25% of GDP, then the results are quite a bit more beneficial, and it looks like the world could escape the crisis. Now, who knows if this is true? This is a very simple-minded model which is run out on a computer. And, but it does have some important elements, I think, of the situation that we're facing. So let me give you a quick summary of the key features of the simulations, and then go a little bit of detail into 2 or 3 issues that I think are quite important, and then summarize. So the dynamics is built on 2 or maybe 3 assumptions. The first key important issue is that if you have higher capital per capita, output can go up, and that increases the speed of CO2 emission. I mean, that's sort of just accounting. On the other hand, higher atmospheric CO2 reduces output and growth of capital. So somehow there has to be dynamic processes for growth and for CO2, and there has to be some kind of interaction between these 2 things. Now, those of you who sort of play around with this sort of stuff, this kind of mathematics, would recognize that this is a variation on a typical predator-prey scenario. Predator-prey models essentially are the classic case, talks about wolves and moose, which is very good for a person who lives in Maine, where we have plenty of moose, and the wolves in the form of coyotes are coming back. But the typical scenario then is kind of these populations fluctuate around each other. But what happened in those pictures that I had a minute ago, notice that output crashes, but greenhouse gas does not. And what's going on there, of course, is that the wolf is almost immortal. That is, once the greenhouse gas gets up into the atmosphere, it's going to stay there with a very slow dissipation rate. And that's the sort of central issue, one of the central issues that we have to face up to. There's another issue, which has to be that in one way or another, the economy has to go to a stationary state. That is, the history of capitalism over the last couple of centuries has been a history of growth. Growth in output per capita, which has enabled people in some corners of the world to become pretty rich compared to other corners, and those other corners are now catching up. But that cannot persist. If the world is to be viable after another century or two, basically any ongoing greenhouse gas emission has to be compensated for by mitigation. But you just can't have greenhouse gas going up forever because that will completely destroy the system. So basically the economy and the society have to go to a stationary state with essentially constant capital stock, constant CO2. Otherwise, the system will just be overwhelmed. Now, there are a couple of other aspects of the model that I think are probably worth mentioning. It's a demand-driven model. That is, most of economic growth theory basically assumes full employment of all resources, capital and labor. And that's built into the standard models that all the macroeconomists use. Somebody, let's say, like Paul Krugman or Larry Summers is now trying to back away from that since they recognize that, gee, demand has fallen short of supply for the last 7 or 8 years, and they come up with explanations. But I think it's better to start from demand, just say the world is demand-driven, and that's the philosophy behind these simulations. Now, that requires telling a story about how the economy behaves in the medium run, and then extending that to the long run. The particular medium run story that's built into this specification essentially says that there's another kind of predator-prey dynamics, which is, I don't worry about business cycle fluctuations, but basically the story there goes back to Marx, says that if the economy is at a low level of economic activity, the reserve army is big, and that there's not much upward pressure on wages. If, in fact, the economy starts to grow, then labor's bargaining power increases, which tends to put pressure on profits, and which tends to reverse the upswing. I mean, that's a very old story, and that's the sort of medium-term adjustment story that we have. Now, basically then, I'm assuming that profits, investment, and output are squeezed by rising CO2 concentration, and that's another important aspect of the specification. There's another issue, which I'd like to mention, that is the simulations are set up to go to, as I mentioned, a stationary state. But that means that productivity growth has got to go to zero. Productivity is traditionally measured essentially by output over labor, output over person hours, output over the number of people employed. And the key to modern economic growth has essentially been growth in labor productivity. Now, where does that come from? There are a number of economic theories which I don't find terribly convincing. I think Duncan finds them more convincing than I do. But what went into this model was the idea that comes from ecological economics, that the real key to productivity growth over the last couple of 100 years has essentially been throwing energy at labor. That is, you find ways to use more energy in various ways, combine that with labor productivity goes up. You'll recall that toward the end of Anna Karenina, Levin goes out and begins to cut the grain with his peasants. And there are a lot of peasants cutting the grain along with Levin. And so that is that each one of those peasants is using a couple of hundred calories. Fast forward 100 years, or even 50 years, and you've got a guy on a combine harvesting much more grain, using much more energy. I mean, that's to a large extent, that's been the story of labor productivity growth, and it's one that cannot continue. I mean, this is, again, an old idea in ecological economics. Kenneth Boulding, Herman Daly, Martinez Allier have all made this same kind of point, and it's one that we chose to build into the model. Here you see a picture, which is due to another New School graduate student, Gregor Semyanuk, essentially showing relationships between between productivity on the vertical axis and the use of energy, the energy-labor ratio. And there's a pretty clear positive slope over time and across countries. I could go into much more detail on this, but I don't think there's any reason. We can pursue it in the questions, I guess, if you want to. Now, here we come to maybe something I don't want to talk about, given that we have fairly limited time. But let me just show you a picture. Suppose you get to a stationary state where capital per worker, capital per population, and CO2 are constant. And then you could think of trade-offs that would hold those growth rates to zero. That is, you've got these two variables, capital population ratio, capital per capita, and greenhouse gas. And there are various combinations of those that could hold capital accumulation to zero and greenhouse gas growth rate to zero. Those combinations in the jargon are called null-clines. And if you want to know the etymology, it's null, which means zero, and cline, which is a Greek word for slope. So basically, the null-clines give you combinations of those two variables. If you look at the solid red line, that says that it's business as usual. There's some kind of trade-off that will hold. If you look at the solid red line, there's some kind of trade-off that will hold greenhouse gas emission to zero. And notice that has a steep positive slope. If you do some mitigation, the slope becomes much more shallow, the blue dotted line. And that essentially says that you can mitigate and get to a higher level of capital per capita on the horizontal axis and a lower level of greenhouse gas. So that's just a way to play a game about where the economy is going. And then we do some simulations. Here is, again, a simulation of business as usual. Again, you get growth of capital stock per capita for 70 or 80 years. There's a collapse, and then you settle down to something relatively low. Notice employment. The employment population ratio in the middle there, labeled lambda, in the middle of the diagram, starts out at something like 0.4, and then goes down steadily and stabilizes at something like 0.15. So basically, you get a lot of unemployment as a consequence of the output crash, which is not terribly surprising. That is, again, mainstream models don't let that unemployment happen because they assume that it cannot. But I think it's probably a fairly likely outcome. Labor productivity, energy productivity toward the bottom rise for a while, and then we assume that gradually the throwing of energy at labor dissipates or goes away. And so both those variables stabilize, and that gets you to the stationary state. Then we can worry about mitigation dynamics. You could look at a cost prize of trying to mitigate emission of CO2. And for the mid-range of estimates nowadays is that spending $160 per metric ton of carbon on mitigation will offset that carbon emission. That's $44 per ton of CO2, and that's more or less the mid-range of current cost estimates. Frank Ackerman, who is here, knows this a lot better than I do, and may want to say that I'm wrong. But anyway, these are the kind of numbers that we were using. So then, with the mitigation, as Duncan was saying, with a mitigation output of maybe 1.25% of world output, which is around now about $60 trillion, CO2 concentration can be stabilized. Now, this gets you then to the kinds of policy questions that Duncan was talking about. That is, 1.25% of world output is around 1/2, bit less than 1/2 of the current level of defense spending. Now, defense spending is obviously vital to the survival of the world economy, society, et cetera, but, it's a lot of money. And whether there would be political consensus to do that kind of reallocation of spending is, I think, an open question. Interestingly enough, it's roughly twice the level of worldwide energy subsidies. That is, if you look at subsidies to energy across all countries in one form or another, they come out to be about 0.5% of GDP. So then you get these transient paths to steady state. This is the same diagram that I had before, essentially showing that with the green line, greenhouse gas concentration roughly stabilizes, output grows, employment goes up a little bit, et cetera, et cetera. These results are largely driven by the time behavior of the accumulation equations for capital and for greenhouse gas. That is, these processes have a certain timing involved. Output per capita for the last couple of centuries, century and a half, at least in rich countries, has been growing by about 2% per year, 2.5%. So that, there's a sort of time scale built into capital accumulation. There's also a time scale built into the greenhouse gas emission. Back in 1850, there was not a lot of greenhouse gas emission, simply. People were starting to use energy intensively, but nevertheless, the growth of greenhouse gas from a very low level was pretty slow. It's been gradually speeding up, and the interaction of those time scales is what's giving rise to the crash that some of the other simulations were showing. There's another way to look. There are other ways to look at this situation, of course. One would be to accept a neoclassical model. Just assume that there's full employment. There it is. And that is usually given the label of the Solow model after the now nonagenarian professor at MIT, who taught most of us economists in this room. And notice that the path without carbon being present for a demand-driven model is the green line, and the Solow model gives you the green line at the top. The Solow model gives you the red line at the bottom. Red line 2 steps down. So the dynamics is basically similar, both with and without mitigation in the Solow model and the demand-driven model. Again, I think the interest in the demand-driven model is it puts more focus on income distribution and also permits unemployment. So let me close with just saying a little bit about the impacts on labor. That is, the business as usual stationary state is employment population ratio is 65% below its initial value. That is, G skyrockets, output stagnates, and productivity continues to grow until it stabilizes. So that ratio lambda falls by a lot, by 2/3, in the business as usual scenario. If you do mitigation, then it can rise a little bit. As it turns out, the share of wages in output, just by accounting, is equal to the real wage divided by productivity. Now, the share of wages tends to stabilize, the share of profits, which is what the diagrams show, tends to stabilize, which means the share of wages tends to stabilize, which means that the real wage can grow roughly as fast as productivity. So then what you get in business as usual is a high wage and low employment economy. And how that would be resolved in socioeconomic terms is very much an open question. The mitigated solution at least gives you high wage and high employment. The stationary state still is a zero-sum game. That is, output per capita in a stationary state, output per capita is going to have to be constant, which means if somebody gains, somebody else loses. So it's zero sum in that sense, but at least if you have mitigation, it would stabilize at a fairly high wage and fairly high employment, which would make the social issues perhaps slightly more tractable. But in any case, even with mitigation, the world is going to face a pretty severe sociological, political readjustment. And how that works out, I think, very much remains to be seen. So in any case, this sort of the work that I'm reporting here has been supported by the Institute for New Economic Thinking, which is an outfit in New York that does good things from time to time, and maybe not such good things. And it's been helped by a lot of people, many of them at the New School, who did all the work and most of the thinking. So let me say thanks to them as well.
Okay, thank you, both Lance and Duncan. We have a reception immediately after this, but first we have some time for question and answer. So could I ask both Duncan and Lance to please come up here? And can you please wait till I give you the microphone before you ask your question, because we have some folks also watching us online. So who has some questions?
Hello, and thank you so much for the information I gained from your presentation. What was the mathematical method for solving the equations?
We used a differential equation solver from the program package Mathematica, which is convenient to use and powerful.
So there's this, carbon dioxide is the predator, and it destroys the prey, which is capital per person. What exactly is the mechanism there? In other words, I get it that our last winter has reduced output in Boston, and I also get it that if we wait long enough, we're going to fry ourselves. But kind of over time, what's the actual mechanism that the CO2, or mechanisms that destroy the capital stock?
Well, the mechanism in the model essentially says that there is a damage function. The way the thing is set up, CO2 emission, or CO2 concentration, cuts into profitability, which then reduces investment and ultimately leads to the collapse. Now, the way it cuts into profitability would essentially, you'd have to say, that a lot of the things that the higher carbon dioxide concentration will create, for example, more storms, more difficulties with transport, sea level rising, which is going to flood New York City. We can push the damages down in that direction. There are a number of factors like this which ultimately will come together to reduce profits and also investment demand. Now, there's a variant of the model which says, there's another set of simulations we did, which says that the effects of rising CO2 concentration is essentially destruction of capital and faster depreciation of capital. And one example which happened to spring to mind a few years ago is suppose that a Category 5 hurricane hits the Houston ship channel, where about 15% of US refining capacity is. So if that were to happen, then there would be massive capital destruction, and basically that would also have the same effect. So, you know, this is a shorthand macro model, and if you're going to do it right, you'd have a detailed micro model which would trace through some of these things, but that's not what we did.
So I think this is great. I remember hearing you present this at a New School seminar last year or a year or two ago, and it strikes me as intuitively believable and yet strangely specific in some ways. So I remember wondering about the 80 years, whether this was a parameter that you put it basically is the 80 years an input or an output. And because I had the feeling the last time you presented it that that was a parameter choice you made that determined that that intuitively believable surge lasts 80 years rather than 40 or 120. And the other thing which struck me this time is that you went straight from the fact that greenhouse gas concentrations can't rise forever to the statement that capital stocks can't rise forever, which seems to assume something about limits on decoupling or the possibility of a zero carbon economy, which, there's certainly a lot of technological speculation about the possibility. If you could fully decarbonize the economy, would that release the constraint on capital stocks? If you could incremental capital stocks used no additional carbon emissions, would you then be free of the limit imposed by the obvious physical limit on greenhouse gases?
Yes, I'd have to think about that, but intuitively that sounds plausible. But the question is, can you decarbonize the economy, given the fact that there's been such a long time period in which we've essentially built productivity growth around throwing energy at labor. Now, the 80 years. That is CO2 concentration and capital per capita essentially interact through a damage function. And the damage function, if we play with the damage function in the simulations, that doesn't change the 80 years, 70 years by very much. So my feeling is that it's more built into the dynamics of these two processes. Which are basically accounting dynamics, and the time frame of the two equations is such that you get 70 or 80 years. You could make it go down to 60, up to 100, something like that by playing around with the damages, but that sort of peak and then the decline seems pretty much built into the accounting, if you like.
Well, I would underline the point that Lance made about the inherent growth rates of capital accumulation and greenhouse gas accumulation, which I think underlie that rough time scale. And I would certainly caution anybody about taking any of these simulations as more than a pretty rough guess. However, I think that particular part of it is not, of course, it's easy for me to sit here and say that, but what's going to happen 80 years from now? But I have a feeling from our playing around with parameters that that's a fairly robust aspect of these simulations. This question of how you treat the substitution of non-carbon energy sources for carbon energy sources is formally a little bit complicated. Maybe we need to do some more work on clarifying that. At the moment, we treat that as part of mitigation. Effectively, that's treated as a subcategory of what we call mitigation. And therefore, the mitigation costs would include any increase in cost for moving from carbon-based to non-carbon-based energy sources. And those simulations then come to a steady state, not because of climate damage, but because population and productivity growth asymptote. And that's that's not an endogenous stabilization. That's imposed by the model.
Is it on? Everybody can hear me. I guess this question is addressed more to Lance. You seem to be getting a great deal of mileage out of climate change somehow producing long-run unemployment. Right? And can you speak a little bit more about why climate change produces long-run unemployment any more than crowding or congestion or population increase or anything else out there? And why doesn't it correct itself?
Well, again, that's, I guess my immediate answer would be how you think the world works. That is, I really do believe that the way the macroeconomy operates is that it's largely demand-driven, so that unemployment is possible. And if it's demand-driven in such a way that productivity growth is still continuing and output collapses, then you get unemployment. Now, the possibility of unemployment is simply ruled out in the Nordhaus model or the kind of stuff that Nick Stern does. And it seems to me that that's just the wrong way to look at the world.
Could I venture slightly more? I think if you look at the nuts and bolts of it, it also has to do with the what's called the distribution relationship in these structural growth models, and the interaction of the distribution relationship, which has to do with how the profit share reacts to employment levels and the need to achieve just the right amount of investment to keep you at the steady state.
There was a comment made about technological disruptions in the past. And of course, there was a dramatic one just over 100 years ago when we went from horses and buggies to automobiles and from gas lamps to electric lamps. And the outcome of that turned out, from an economic point of view, not to be so bad.
Yeah.
Right? Now, if you compare that, though, to we now have all these climate externalities that are occurring, and the cost of those is clearly rising over the years. What sort of what will lead to the, I don't know, I hate to use the term tipping point, whatever it is, where that will be perceived by the existing economy and the thinking about the economy into a transformation that would actually either both mitigate, and obviously we'll have to spend an awful lot of it on adaptation, resilience building, and so forth. So how are those pieces going to play out in your thinking in the future?
I get to answer that one. This is a very very well-informed audience, of course, and so the questions are very, very good ones and very pointed ones. Well, I think I was the one who raised the parallel to these past big adaptations that we had to make to technology, and I would defend that. I think it's a big thing to figure out how to wean yourself off of fossil fuel. There are people, for example, at the Santa Fe Institute, I've encountered people who pretty much think that the rise in standards of living over the last 250 years are almost entirely the result of the injection of fossil fuel energy, and put very little weight on what Marx calls social relations of production, or reorganization of labor through, say, Smith's division of labor types of effects. Well, if you believe that, then it's a pickle. I mean, then you really got a very difficult transition, because it's like you've been operating with some kind of a nervous stimulant that you can't take anymore, so because you've become addicted to it or something like that. And then the question is, what do you do? Well, this has back to the half full glass of water, I guess. I tend to think that while the fossil fuel injection was extremely important, and I would be very reluctant to downplay that. It seems to me that Lance's own formulation, in which he said, well, it's the addition of energy to labor. He didn't say carbon-based energy to labor. He said energy to labor leads one to think that you can still maintain at least pretty high standards of living through an adaptation and a process of change. And that's would be my vision of how things would go. I don't think this is going to happen easily. I mean, we have a huge infrastructure built up around carbon energy, and to transform that, for example, in the United States, I talked a little bit about the need. You're going to have to change housing patterns, for example. Changing housing patterns, because we can't be as spread out as we are. We're going to have to live more compactly than we do. Well, housing has a very long time horizon of its own, not as long as greenhouse gas warming, but a long one. And so you don't depreciate the housing stock that rapidly and rebuild around more compact settlement. But you know, human life does go along, and the decades do roll by, and you do transform a lot of this stuff over a finite time. And if it just, the main thing is to point in the right direction.
Right, next question, please.
There's somebody back there.
I had two questions. First, Duncan, could you talk a little bit about the political economy aspect? I mean, how do you think human society will, or what kind of groups will be there to take this issue up and argue for it and implement it? So could you talk about that? And I had a question for Lance. In your model, was there any role of technical change? I mean, as costs change, is there a way in which that feeds back into the model? Is there a mechanism by which people take account of the fact that as emissions are increasing and the stock of carbon dioxide is going up, it is having a negative impact?
Shall I? Well, the political economy of this, I think, is very important and very fascinating. But I think it really helps if you start from accurate welfare economic analysis. This is a kind of a public goods problem. The difficulty with the allocation of public goods is not that there's no incentive for individuals to invest in public goods. There's just not a big enough incentive. So people will provide public goods because it helps them personally, but because they don't take account of the spillovers to everybody else. They invest you get an equilibrium where the investment is at way too low a level. And curiously enough, I think we see this in terms of the global warming, that one phenomenon is that even large corporations realize that it is in their own interests to do some mitigation. And you see these programs, and you could dismiss them as just public relations, but I don't think that's really true. I think these people made very careful, I mean, if you're a really big company, then you are going to start to see some of this effect. You are going to internalize some of the externality. Same thing is true, is happening for big regions of the world. So you get something like the European Union, although it kind of got all thumbs about it, as it tends to do, but they'll sort it out after a while. I think is taking steps to mitigate, to set up a cap and trade system within their own boundaries, and that internalizes a considerable part of the externality. Even in the United States now, Obama has decided he's going to do it by executive order. So it's really not the case that there's no constituency for doing something about it. There is a constituency, and people do recognize the net benefits of doing it. The problem is to coordinate so that you get the full benefits of a coherent mitigation system. I think that's, well, I'm going to say one more thing about the political economy. I was talking to Brian about this before. And this is very explosive, maybe this is the controversial part. There's a temptation to link solving the global warming externality with redistributing world income, because these are two big problems. And we have a very unequal distribution of world income, and also in class terms within nations. So it's very tempting to say, well, if we're going to do a big institutional change like cleaning up global warming, why don't we at the same time use that mechanism to redress these imbalances in inequality? I would warn against, be very careful about that, because that greatly complicates. If you just look at the simple welfare economics of an Edgeworth box or something like that, or a utility possibilities frontier, you can see that when you try to push people down below their current reservation prices or their current reservation utility levels, that's when it becomes extremely difficult to get agreement. Then you're not dividing up a surplus that everybody gets some of. You're really going to take something away from somebody else. So I personally think if we want to focus on the global warming issue, the best thing to do is, if not completely, at least to some degree, to decouple that from the concern about world inequality of income. Just on political grounds, basically.
Okay, with regard to the other question, when economists, macroeconomists who commit many sins, talk about technology and productivity, they're essentially just looking at ratios. That is, the ratio of output to labor is labor productivity, the ratio of output to energy is energy productivity, and then you could look at sort of energy per labor. And these things interact. There's a simple identity that ties them together. And in terms of the way the model operates, labor productivity is driven by energy intensity. That is how much energy you're throwing at labor. That was just built into the specification. And depending on how strong that reaction is, energy productivity, output per unit energy, may or may not, may go up or may go down. In the recent period in the rich countries, energy productivity has in fact been rising along with labor productivity. That's less true in developing countries and was not entirely true historically. So in terms of this simple accounting, there's some interactions there that the one simply has to take into account. The way the model works, rising labor productivity essentially for a given level of output, rising labor productivity throws people out of work. The reserve army gets bigger, which means that profits can go up, which means that growth can be faster. That's the linkage between the distributive linkage that ties productivity and output growth together, which is, as I say, goes back to Marx. It's a very old notion.
I'd be curious to get both of your thoughts on the fossil fuel divestment movement, either as a political strategy or the economic thought behind it.
Well, actually, the New School turns out to be on the forefront of that and has actually adopted a fossil fuel divestment strategy.
Of course, it has no money.
It's not a whole lot of money that's involved, and there's also the question when you're dealing with the New School, whether the New School didn't get talked to by some very smart investment advisor who said, you should get out of fossil fuel anyway. It's a lemon, and you should, and then the president said, well, gee, if we're getting out of fossil fuel anyway, why don't we get the credit for doing that? So there are arguments about, there's a constant argument about boycotts and divestment strategies. The immediate effect of divestment strategies is to raise the rate of return to those investors who are willing to hold on to that particular kind of investment. Now, so you've got to trade that off against whatever political advantage you think you're getting. It's not probably possible to force the world away from fossil fuels just through, even if you had a very widespread and very vigorous divestment movement by itself. But divestment is a way to raise consciousness, is a way to get people to think hard about what I think are the more relevant political issues, which are these compensation packages and a political coalition behind that will push implementation of that could be important. You have?
I don't have anything to add.
We have time for a couple more questions. Anyone wants to?
Hi, thank you. My question goes back to the model results and is just, I'm curious why you extended so far in time the model results and your x-axis in particular. I think understanding the the use of this kind of system dynamics models in general, I see the utility of the first part of the model and showing us potential trajectories, but that the part where it levels off for centuries, I'm a bit more skeptical of. In particular, my understanding is that the structure really drives the dynamics in the model, and after such a big crash, do you think the structure would really remain the same?
No. But I mean, one does what one can do. I think as I've said several times, the sort of run up until the crisis, the timing of that is sort of basically built into the dynamic processes of output growth and CO2 accumulation. So that, I think, is in one way or another, if there's no mitigation and if business as usual, et cetera, if they continue, I think it's pretty likely that there will be a crash at some fairly distant future time, say one human lifetime from now. That's certainly something that I think is built into the accounting. Now, after the crash, we simply built in a stationary state. The way we built in the stationary state was to assume that world population growth would go to zero in something rather more than 150 years. And then we built in the productivity growth around that population projection. So insofar as, running these things out for many decades, obviously it's not a forecast, but at least it lets you think about the logic of the situation.
Yeah, I would agree that mostly those long tails are there to represent the stationary behavior of the model. The only other thing that I'd add to what Lance said is that there is another long time constant that's inherent in this process, which is the half-life of CO2 in the atmosphere. And that is on the order of, what, 300 years or something like that?
More than that. Well, we had...
Half-life for...
half-life was on that order.
250 years or something. So it seemed like it was not completely egregious to think about what the really long-run behavior is.
I wonder if you have any comments on how your model and its predictions compares with the Club of Rome model, and which has also been updated in recent years.
I have not looked at the new Club of Rome, and I probably should, I guess.
Well, they had predicted all sorts of things going downward by 2020.
Yeah.
And they say they're still on that trajectory. So they have a much nearer crash than you do.
I can see how, again, I haven't looked at it, to be honest, but I could see how that could happen if you took into account some of the other horrible things that we're doing to the world. I mean, the water would be one. Conceivably, species extinction could be another one. pH in the ocean. There are a number of shorter-term processes that are going on out there, which could hasten the crash. But again, this is a very simple-minded model, and was only looking at CO2.
I can't resist telling a little story which may have something to do with both education and modeling. I was at MIT, teaching at MIT in the late 1960s and early 1970s in a program called Concourse, which tried to have an interdisciplinary unification of the freshman program at MIT. And we had this group of very bright MIT students, and one of the things that we did as an interdisciplinary project was to replicate the Club of Rome, because that book had just come, the Meadows Forrester book had just come out. And we began by giving the students a little questionnaire before this module, which asks such questions as, was there overpopulation in the world? What were the dangers of overpopulation? How would you know about it? And stuff like that. And then we taught them a solid 6 weeks of population theory and the Meadows-Forrester methodology, and we taught them how to write programs in the Meadows-Forrester, and we gave them assignments to take the Meadows and Forrester model and turn it into a utopian instead of a dystopian model by changing the critical feedback parameters. And they did all that, and then we gave them the same quiz at the end, and it turned out that they had exactly the same opinions, except they weren't as interested in the subject. And we then sort of debriefed them a little bit about this and asked them what they thought they learned during the course. And they said, oh, that Forrester Meadows model was great. That was a really good thing. That was a really good unit. And we said, why? We taught you that it was junk science, that you could get anything out of it by fiddling with the parameters. And they said, yes, but we know how to do that, and other people don't know how to do it.
Thanks to both of you for interesting talks. It's a little difficult as somebody who doesn't know these models to try to understand from 15 or 20-minute talk if these really, really complex models that you're presenting. So I'm sure I'm not the only person here who's sitting thinking, I missed a couple of equations, maybe a couple of hundred equations in this picture. Duncan, you referred to, or you alluded to, these compensation packages, but you didn't actually talk much about them. At kind of early in the talk, you said something about, well, if we change strategies, there are going to be some losers, particularly loss in the value of assets. And the first thing that came to my mind is, yeah, the oil companies are going to lose a whole lot of money if we suddenly shift to a lower carbon strategy. So I guess the bigger question is, who deserves to get compensated, particularly since you're concerned that we're looking at income inequality globally, and should we not be messing around with that along with issues of climate change? But there's you had some reference to compensation packages, so I'm wondering if you could talk about that. And Lance, you keep talking about demand side model, or demand-driven model, and I'm wondering if you could explain a little bit more. Right now, the Globe is saying every contractor in Boston is busy, and if you're hoping to have your deck fixed, forget it, because demand is so strong after what has been a climate-induced crisis. I'm wondering if you could just talk a little bit more about the assumptions about maybe wealth-determined assets decline in value and wealth drives demand. I didn't get the demand side of that.
I think the compensation thing is really where the next step to go, and I especially would address this to, say, Fletcher students and stuff who are here, who are working on the politics and diplomacy of these kinds of issues. Let me just very briefly take two cases. You're going to raise the price of gasoline, let's say at $8 a gallon. Well, is that going to be popular in and of itself? No. It's going to be there's going to be a lot of anger and outrage about that. Now, how do you, in principle, the economic theory is telling us we have the resources in this package to give compensation for that. The compensation cannot come that we'll give you the money back at the pump, because then you'll just use the same amount of gas. So you have to give the money back in the form of a broad tax cut or the provision of other services, way better public transportation or way better public education or way better health system in some way. And it has to be packaged in such a way that the electorate sees those two things as connected, so that they're not just separate things, but that they're actually connected together. And that's a big challenge, and I agree with that. Now, on this question of how much should you pay off the owners of fossil fuel reserves, Well, I agree that this verges on issues of extortion more than of economic efficiency. So, but you know, speaking for myself, if you have to buy off some support to get political consensus, I don't think that's anything new to the American political system or the world political system. That's how you get political consensus, and sometimes people who don't deserve it get money as a result of those processes. I would like to see it minimized, but if some money goes to the wrong place and you still get the emissions under control, I may not lose a whole lot of sleep over that. I don't know if Lance, yeah.
Well, let me try the other question. What I'm trying to say, I think, is that to a large extent, the level of economic activity is decided by demand. I mean, what you spend is what gets produced. Now, I'm not saying that there are never supply constraints. I'm sure you're perfectly right about contractors in Boston. And, if you're sitting in Brazil right now and your Chinese market is shrinking, then you're going to be short on foreign exchange, and you're going to have to cut something back. But I think certainly for rich countries on the whole, my general perception, which is not the standard perception, it is that really, as I say, what is spent is what gets produced. And that essentially is a demand-driven economy. The demand responds to various things, profitability and income distribution and several other factors. But nevertheless, I think that's the key. Let me give you another example, also regional. Rural states in the US, people who drive, and you have to drive, use about 1,000 gallons of gas per year. If you were to raise the gas tax without doing anything else, if you were to charge, say, $5 more per gallon for gas, which in a way would be a perfectly rational thing to do, you know, that's $5,000, probably more for a family in a state like Maine. That's a lot of money. I mean, if your family income is like $30,000, and all of a sudden, and you have to drive your pickup, you have to spend another $5,000, $6,000 on gas. You know, that's going to clobber demand and output in Maine, and that's why compensation at that level becomes a critical issue. If you want to raise the gas tax, then you have to compensate rural Mainers by a lower income tax or something like that. So these issues, distributive issues, are very much built into the whole problem.
Okay, let's thank both Lance Taylor and Duncan Foley for coming to be with us today.
Is this the right one for me? Yes.
You finally get your award after this long evening of answering questions.
Oh, we
thank
get a
you so
reception
much.
also.
Yeah, you get a reception. Thank you very, very much.
Thank you.